Good afternoon, all. I, Irti Telang, Assistant Professor from Delhi Technical Campus, welcome you all on the sixth day of Atal FGP on recent trends in deep learning and large models. Over the past few days, we have had enriching sessions, insightful discussions, and valuable interactions. And today promises to be no different. Your presence and enthusiasm continue to make this session a wonderful session. Without further ado, I would like to introduce our speaker for today, Dr. Seema Verma, who will guide us through an insightful session. Dr. Seema Verma currently holds the position of professor and head in the Department of Computer Science and Engineering at Delhi Technical Campus of Computer Science and Engineering at Delhi Technical Campus, Greater Noida, India. With over 22 years of rich experience in academia and research, she attained her MTech from JC Bose University, Faridabad. She attained her MTech from JC Bose University, Faridabad, where she achieved the prestigious distinction of being a gold medalist and is also UGC net qualified. Her academic journey culminated in a PhD from Thapar University, Patiala, awarded in 2015. Dr. Verma has made significant academic contribution through numerous publications, 5 patents, and a Best Paper Award. She has organized and convened national and international conferences and served as an editor and speaker for several academic works. Dr. Verma is an active member of the IEEE Society and a life member of the ISTE Society. Her research interests encompass artificial intelligence, machine learning, and information security. Let's begin the session and make the most of today's learning opportunity. Thank you. Ma'am, please.
Thank you, Iriti Madam. Very good afternoon to all. I'll be delivering the session on Generative Adversarial Network for Creative AI Solutions. Iriti ma'am, am I audible?
Yes, ma'am.
Thank you for the confirmation. So we'll be learning a Generative Adversarial Network and so generative AI, will be starting with that. It refers to a class of artificial intelligence technologies designed to create new content. These systems learn from patterns in existing data and use this knowledge to generate novel outputs. So the key idea is that the system can understand and replicate underlying patterns in various data types, whether it is text, images, audio, or even video itself. And the primary goal of this generative AI is to enhance automation, creativity, problem solving abilities by it will be replicating actually or augmenting human-like creative processes. We can take the examples. For example, text generating written content like articles, summaries, or even poetry itself. Images creating realistic or abstract images, art and visual designs. In music, composing original music in different genres and styles. In video, of course, generating video content, including animations or even deepfakes, as we are aware of these terms. So these capability is revolutionizing creative industries by enabling rapid content creation, personalized experiences, and innovative solutions that were not possible before this. So the core objective of generative AI is to enhance human creativity and productivity. By automating content generation, it helps in replicating or augmenting human-like creative processes, which leads to the better design, media production, and scientific research. We can take the example we are using like Dell E or ChatGPT. which are autonomously generating images based on text prompt. We are giving the text and it is generating the images based upon that. Also, artists and creators are now using these tools as creators, which are enhancing its capability to generate better designs, and of course, it is saving their time. So we can talk about a few of the key generative AI technologies in which, for example, large language models like GPT-3, GPT-4 are at the core of many generative AI applications. And they are excelling at understanding and generating human-like text, enabling chatbots, content creation, summarization, task, etc. Then in next, if we are talking about small language models, these are smaller but efficient version of LLM itself. These are often used in edge devices. For example, low resource environments, if we are having, we can use that small language model. For example, digital BERT, which is the optimized version of BERT itself. Next model, we can talk about retrieval augmented generation RAG. RAG enhances generative models by integrating them with the retrieval system itself, as it enables them to fetch and generate accurate and context-aware responses. Of course, this is very useful in knowledge-driven tasks. Variational autoencoder, these are probabilistic models that learn latent representation of data. They are used for tasks like anomaly detection, generation variation of images, or even drug discovery itself. Generative adversarial network, it consists of two neural network, generator and discriminator. These works against to each other and they are widely used in image synthesis and style transfer type examples. Next, diffusion model. These models are really revolutionizing the image and video generation. They work by gradually removing noise from data to synthesize new and realistic output. So this is improved version of the previous, we can say. Reinforcement learning with human feedback. Actually, this technique fine-tunes AI system using feedback from humans. It plays a key role in aligning AI with user expectation and ethical consideration. Lastly, we can talk about multimodal AI. Multimodal AI integrates multiple data types, for example, text, images, audio, to generate complex outputs. For example, include AI system that caption images or create videos based on textual description. We are giving the text, and according to that, any media can be generated. So these technologies working together or individually, of course, we can use them both ways, are the backbone of generative AI. So we are starting with the generative adversarial network. The GANs consist of a generator network that generates new samples and a discriminator network that tries to distinguish real from generated sample. So in this, we are using two neural networks which are working against each other. So they are trained in adversarial manner. That's why this word is given to this generative adversarial network. So this is the magic of GAN. We cannot distinguish between the real and the fake images, we can say. First of all, we will be covering few applications of generative adversarial network. For example, it's generate realistic photograph, landscape portrait are shown here. Generates examples for image data set as digits are there, some faces are there, some other pictures are there. It can generate examples for example, this is the data for a particular for some rooms actually. We generate examples for again image data set. For example, we are having the data man with glasses and we are having the data man without glasses. So, and we are having the data woman without glasses. So what we can do, we can have this particular data first man with glasses, then we can remove man without glasses and we can add the female face with the glasses. So result can be woman with the glasses. So this can be possible with the help of this generative adversarial network. We generate photographs of human faces, different types. Again, it depends upon which type. So it is successful in generating all these types of human faces. Again, few examples. Again, it can generate cartoon characters, some anime faces, cartoon creatures, comic scenes. These can be generated with the help of generative adversarial network. Then these cartoon characters, these again Pokemon characters are there in this image. Next is image to image translation. This is one other application of this GAN. It sketches the photo and maybe it can convert day type photo to a night type photo. And it may be black and white photo is there and it is converting it into colored photograph. This is the example for that image to image translation. We are having a particular image of daytime and it is converting that into the nighttime photograph. Again, other example of image to image translation, we are having the framework, we can say, structure, we can say, and we can convert that into some real photograph of that. So other one, it is again, it is converting it into, for example, some animal is there, some other animal is there, and in the third one, it is converting it into the combination of both of these. Horse, zebra, and then it is a combined feature. So these can be generated with the help of generative adversarial network. Again, it can be generated that painting to photograph, it can be converted with the help of GAN. So other application is text to image translation. GAN can generate images from textual description. So like we have written, this bird is black, the with green and has a very short beak. So it might be that we can write it with the features and it will be generating the images according to the features we have written over that prompt. Another example, it can be we have given some features to that beak must be here and belly must be there, right leg must be there, and the images can be generated according to the conditions we have given. Semantic image to photo translation, it is here, some photograph is there and some real photograph can be generated out of that. Then different views can be generated with the help of this generative adversarial network. We can have that right view, left view, and again different views we can generate. Then again, different poses can be generated with the help of this GAN. We are having the original one and different poses can be generated with the help of this generative adversarial network. Semantic image to photo translation. We are having that photos and like this is the input photos and it can be generated. It can be converted into emojis. Then it might be we are having the real image and we are reconstructed that image with different hairstyle, for example. So we can change the style also. This photograph is with blonde, bangs, smile, and male. We can also change the features as the face is reflecting as male features. Then again, this is actually based upon the age factor. So again, can reflect that a particular real image into different age, the same photograph with different age. This is another very good example. We are having the picture with rain and we can convert that picture without rain. So we can edit and manipulate it. Again, we can take that. For example, we are having this original one and we can convert that into age-wise category. So this is the face which is reflecting this particular age and till 29 and 60 plus and so on. So we can have those features with the help of GAN. Then again, we are having variation with the original face. Then photo in painting and restoration. Of course, we are having, sometimes we are having damaged photo. We are having some photo which is not complete. So we can make the complete photo. For example, we are having low quality photo and we can improve it with the help of GAN and it will be with the high quality photo. Then it may be that there are some missing part in the photograph, and we can complete that with the help of that generative adversarial network. Then it may be with the clothing translation. For example, we are having a particular any person now, and he or she wants to try some particular dress, and it may be giving that particular variation with the help of GAN. That's this dress with uh, a person with different types of dress. It can be shown as a demo. Then video prediction. So it can GAN also can help with the video prediction also. It can generate videos also. It can predict the next frame in that sequence of video. 3D object generation with the help of 2D images, it can generate the 3D view of that particular photo. So we are having endless possibilities with the help of GAN. It can open a world of possibility which you can think and you can generate with the help of generative adversarial network. Now we'll be going into the technical details of the GAN. We are having actually two neural networks. One is the generator. One neural network can be named as generator, and another that other neural network can be named as discriminator. So generator, it generates new samples from the random input. We'll be taking the random input and it will be generating new samples from it. So the objective is to make them indistinguishable from the real data. Then discriminator neural network, it will be trying to classify samples as real or fake, whether it is real or fake. And it will be providing the feedback to improve the generator. So both of these neural network will be given the training so that it will be generator will be trying to fool that discriminator. I'll be explaining it. So the main purpose is to fool the neural network, visualizing new pattern, and adversarial training. These three things are involved in this GAN training. So as we discussed, generator, it generates fake samples. It tries to fool the discriminator so that it will be generating the data so that so that the other neural network will not be able to distinguish between the real and the fake. So, and what discriminator will be doing? Discriminator tries to distinguish between real and fake samples. Then these will be trained against each other, and this step is repeated again and again so that generator and discriminator will be improved over the period of time. So we can have one example to again understand this GAN's architecture. We can think that a person is there who is generating the fake note. He is considered as a generator, and there is a policeman or cyber officer who can distinguish between that this note is real or fake. So generator will be trying this fake person or thief, we can say, he will be trying to generate the note as real as possible. And the task of this police is to distinguish whether this generated note is real or the fake one. So this is the neural network which is acting as a generator, and this is the discriminator, which this police is the discriminator, which will be distinguishing between the real and the generated data. So generator will be trying that, discriminator will be always giving yes value to that generated fake note. And what discriminator will be trying, that it will be capable to tell that the note is real or the fake. So both of these person will be trying to maximizing their own benefit. So basically we can say this generator will be trying to make this police as fool. So generator and discriminator both are trying to have the adverse training for that, because for the same note, generator will be wishing that this must be real, and this police will be wishing that it must be fake. So both are working against to each other. This is the GAN architecture. This random, first of all, this real data sample is there, which we can take from again any data set, and generator, some random value will be given to the generator. Out of that random value, it will be generating that particular real data, sort of real data actually. So this generated data, which is generated by the generator, and the real data sample, both are given to the discriminator neural network. Generator and discriminator both are neural network. So this particular real data sample and fake data sample is given to discriminator, and it will be telling that this generated fake sample, this the input is real or the fake one. So it will be giving its feedback again, and it will be optimized as the training goes on. So we can understand this with the help of this figure. We can assume that this side is the generator. It means this is generating fake data. Fine, and this is the real data. So we can take the example of MNIST data set. It is taking some number, handwritten numbers. So generator is generating some number, and there are some real images also. So both of these will be given to the discriminator, and discriminator will be telling whether this generated data is real or fake. So it can be, if it is, if discriminator's value is 1, it means this is real value as per discriminator. So discriminator, if it is giving 1, it means 1 is the value. It means real value. And if it is 0, it means fake value is there. So everything depends upon this discriminator's output. So it depends upon, here we have taken two parameters, theta and phi. G is for generator and D is for discriminator. Theta and phi are the parameters which are used by generator and discriminator respectively. So the main objective is, as we want that discriminator will be giving the value 1, because 1 means real. It is telling that this neural network is telling that the value is real. This is the purpose of this generator, right? So, and if it is giving 0, it means the value is fake. It means that the data will not be accepted as per 0 and 1, right? So the generator's objective function will be to this. It will be what will be the value of this? This score is written over here. G phi z means G is the generated score. Generator will be giving some score to the value which is generated from this this fake value, and discriminator will be giving some score value to the generated value. This is written like this because it is related to the algorithm of GAN. So discriminators, this means discriminators score to the generated value. So discriminators score must be high. This is the purpose of this generator. It must be 1. So it means what generator will be trying to maximize this value d theta g phi z, so that it will be giving one value to this, so that its value, its data will be accepted by the discriminator. So rather than we are writing that d theta g phi z, because it will be maximizing it, will be writing 1 minus d theta g phi z, it will be minimizing it. We can write that. So either we will be saying that this is maximizing this d of g, or we can say minimizing of 1 minus d of z. So one and the same thing for that. So it will be, it means generator will be minimizing that 1 minus d of gz, right? So the, and on the other hand, what discriminator will be doing? So this is, again, I'll be explaining this. So this generator means it is minimizing this 1 minus d theta g phi z. This is again the loss function we are using for calculation of that activity, our objective function. So this is generator's objective function. It will be minimizing this value. And on the other hand, what discriminator will be doing? Discriminator will be maximizing its own value. It means discriminator is having two values, one from real data set and other is from generated set. It will be maximizing this real side, and it will be minimizing this generator's side, right? So if we are saying, and what is the value from generators? The value from generator is d theta z phi z, or it means that this will be minimizing. So if we want to maximize, if we want to write it in maximizing form, we'll be writing it 1 minus of that. So what it will be doing? It will be discriminator will be maximizing real side and minimizing discriminator side. Sorry, generator side. Or we can write 1 minus generator side. So we have written this one here, maximizing this log of d theta x. This is from generator side. Sorry, this is from discriminator side. This is from real data side. Actually, x is for the real one and z is for the fake data. So this d theta x means this is real right side. This data is from the right side. So it will be maximizing this side. And 1 minus d theta z phi z, we have already discussed. This side is from the generator side. Discriminator's value given to the generator side. So 1 minus if we are writing, it will be maximizing it. So the meaning is this discriminator is maximizing this objective function, and this generator is minimizing this objective function. That's why this particular generative adversarial network is working on minimax algorithm. One neural network is minimizing some function and other is maximizing that particular objective function. That's why it is called adversarial network. They are trained against each other. So this is the complete algorithm for GAN, generative adversarial network. Here the first portion is shown for the discriminators, that it is using ascending because it is maximizing it. A discriminator is using maximizing of something and generator is using minimizing of something. So we'll be using, if for maximizing, we have used that ascending its value. We are using back propagation, and it is saying that by ascending it, because we need to maximize it. On the other hand, in generator side, it will be descending it because it is targeting to have the minimum of this value. So it will be using descending gradient optimization, right? So these are the two parts of this particular algorithm. First is working on the maximizing of the objective function, and the second portion is working on the minimizing of the objective function. So this particular, actually, now we can discuss about which neural network and how what can be used out of that neural network. Although we can use any neural network for this generator and discriminator, but at the discriminator, as we know that we need to only distinguish between the real and the fake one. So we can use any CNN for that. But in GAN, of course, we need to generate the values. So we can use very effectively deep convolution GAN. So we can use this network for this. So some guidelines are actually there. Uh, According to research, actually, there are this training is very heavy. We can say discriminator is trained very fast because it is only distinguishing between the real and the fake one. Two values are there, but generator is uh, it is trained. It is taking very long time to train itself. So many researchers have worked on that, and many hyperparameters are taken as a constant one, so that it converges easily and effectively. So some guidelines are there. For example, in this use ReLU activation in generator for all layers except for the output, which uses tanh, and it uses leaky ReLU activation in the discriminator for all layers. So some things are there which are taken as a constant, or in one research it has been written that it must be it's epoch just k, which we have written in the algorithm, it must be 1. So many researches have been done so that it's training can be made simpler. Otherwise, it takes many hours to generate the values. So here we can again show it in the very simple form. Generator, how it is training the data. So generator is there. It is generating some sample values, which discriminator cannot, of course, it at the starting, discriminator is not trained. right? This is real data cases, we can assume, real world images, some data sample we can take, and this is generated value. So both of these value will be given to the discriminator, and the discriminator will be giving that whether this value is real or the fake value. So again, the loss will be calculated with the help of that objective function, and this will be optimized by backpropagation. So here it has been shown that when discriminator is trained, generator is kept as it is. It means both are not trained simultaneously. So first of all, discriminator will be trained, then it will be optimized with the help of various optimization function. After that, when we have trained that discriminator, then that particular loss will be propagated to the generator neural network. And this generator neural network will be trained with the help of, again, backpropagation method. So it will be trained, and while it is trained, discriminator is kept as it is. So these are the training way by which both of these neural network can be trained. So what we'll be doing whenever we'll be using that GAN, we'll be defining a problem. Then we'll be selecting architecture for GAN. It means which architecture, which particular neural network, because we are having many kind of neural network in our literature. So we can use any neural network depending upon our application, which we have already discussed, many applications. So depending upon those applications, we can use any neural network in this. So then after selecting that architecture for GAN, train the discriminator on the real data, that is the real data set. Then generator will be generating the fake inputs, that is from random number, we can say. Initially, it will be taking the random number only, and it will be generating the fake value. So after that, discriminator will be trained on the fake data. First, it was trained on the real data, then fake data was generated by the generator, then discriminator is trained on the fake data. Then after training of the discriminator, generator is trained with the output of the discriminator, depending upon what it is. If it is saying, if discriminator is, of course, it successfully find out that the value is fake, it means generator needs to optimize it itself, so that discriminator will not be able to identify whether the value is real or the fake value. So here we'll be taking some, I'll be showing it for the with the code itself. We can take MNIST training data set, and some random sample is there, generator is there, and it is generating some value, this real data and this fake data. Both of these are given to the discriminator, and if it is giving 0, it means the fake value is there, and if it is 1, it means real value is there. I'll be showing first the coding for that. Just wait, I'm sharing my screen. Please confirm whether the screen is visible. So here I have taken one example. That is again Eminist handwritten digits. Here we can. Sorry, participants. Okay, now this is the example for generative adversarial network for Eminist handwritten digits. Here I have taken that Eminist data set so that uh, generative GANs again. In this particular module, it is working to have the value of this that MNS data set itself. It means real data we are working on. Then some settings are done here. Then basically generator neural network is written over here. And again, those constraints and architectural guidelines have been taken care of, and all the values are set according to that uh, hyperparameters value, which are helping it to converge. So this is the neural network gain for the generator itself. So as this was the untrained generator, we have not set it to train it, or we can say it is not working on uh, optimization of the objective function. So it is plain neural network which we are using to generate the values. So if as we have not trained the value and we have set some random noise for that, so first image it is generating is this particular noise. It means this is not giving any particular relevant value which we are expecting. We are expecting some handwritten digits out of this. So again, discriminator here, again, one CNN is used, simple, in which it is saying that either it will be 0 or it will be 1. So if discriminator is trained, it means it must be having the value uh, 0 for the fake value and the 1 for the real value. As we can see, it is not trained, so it is giving this value as 0.5. It means discriminated because we are expecting, we have used sigmoid function here and we are expecting 0.1 value in this, but it is giving 0.5. It means discriminator is not sure about whether it is real or fake, because it is not in a position because it is not trained and it is not in a position to tell or we can say it is not in a position, it's not capable to tell whether this particular image which has been generated is real or fake. So it is dicey in that sense, and it has given zero 0.5 value at this particular time when it is not trained. Now, after that, this loss function, objective function has been defined over here. That discriminator loss, generator loss, both are defined over here. And after that, it has been trained to optimize it with the help of atom optimizer. So after this training, after this loss function definition, then training is done on that generator and on that discriminator and the generator. So after that, it is generating the value as this one. So after that, it is after training of the data, as we have seen that the first data it has generated was the fake value, not fake we can say, but random. We cannot distinguish between the real and the fake one. Only some random, some dark image was there, which was not including anything. Here we can see that it is something, it is showing 3, 6, 8, something like that. Obviously, it is not again very efficient picture because it needs again further training for it. So this is the final one. It is giving this type of data after using that trained generator and trained discriminator. This is another example. In the previous example, we have shown the images by that MNIST dataset, that is handwritten numbers by that. Here, in this example, because that MNIST data set is taking lots of training, it requires lots of resources, of course, and it takes many hours to complete its training. Here, I have taken a small data set and it took almost 35-40 minutes to train this particular data. So here, the motive is to generate synthetic data for air quality. So we were having some real data as we can we can assume a scenario. For example, in remote areas, we cannot have some apparatus which can be used to this measurement of this air quality index of a particular environment. And of course, we want to have some measures to have that air quality in that particular area. So for that analytics, we can generate synthetic data, and that particular synthetic data can be used to for the analytics department so that they can have some suitable measure for that particular area. So we can generate synthetic data for any kind of application. Here I have taken air quality for that. So here air quality has been taken, and the purpose is, again, the generator and discriminator both are trained, and this is the, because it took almost 40 minutes, so I have already trained this. So here it is showing that this statistics is for real data, which I have referred to from that air quality data, which was available on net. So this real data statistics was there for that particular air quality data, where again different parameters have been written over there, and it has been counted for count and mean value, standard deviation, minimum value 25%, top 50%, then 75%, and max, and for the different air parameters which are considered to be the standard one. So this was for real, these three rows. And the same data, the same statistics has been generated for that synthetic data. So in GAN, real data was there with the description of that particular data. Then synthetic data was generated by the generator, and this particular statistics has been generated and counted, and it has been uh, verified that almost all the parameters, all these things are same, all these statistics features are same as it was for the real data. So we can see here all the parameters have been taken over here. Also, three rows were there. Here also we have taken three rows for here. And we can say three modules actually. All the parameters, CO, NO, then T. So all these parameters, count, mean, standard deviation, these are same as compared to the real data. So our purpose was to have the synthetic data, which is resembling to the real data. Its statistics must be same as that. As we cannot compare number by number. So I have plotted it. So it has been shown over here that in terms of density, real blue is for the real and orange is for the synthetic. So that is generated by GAN. So here it has been shown that almost both the distribution, both the values of these parameters are almost same. So here different CU for CU, then this is for PTU. Almost these, the density function is same for both this synthetic and real data. So another for the verification, this correlation matrix has been drawn so that it comes out to be almost same. This correlation matrix is for real data and this is for synthetic data, and it comes out to be almost same. So in this example, it has been shown that in the previous example, actually, we have shown that GAN generated handwritten data, handwritten digits, which was resembling to the MNIST data set. Here it has been shown that it generated the synthetic data, which is resembling to the real statistics of that air quality. So again, I'm going to my PPTs. So just wait. Just wait for 2 minutes. Hope my screen is visible. Okay. So this actually, this particular PPT is showing that, for example, it has been written in Castle of Ghost in Heaven. So how it is showing? Uh, Let me do it full screen. So it will be giving you the just glimpse of how it giving the results and how it is working. So maybe it is running for 50 epochs, and in first one it is showing this particular uh, photo, we can say image, we can say, and for example we have written Castle of Ghost in Heaven. So this was the prompt given to that particular image generation. Fine. This is not the example of feminist, or this is not the example of synthetic data. It is, again, it is generating the art using VQ GAN. Again, as I have already told you, GAN can be combined with various technologies, and the results can be achieved. So if it has been written, so after, for example, after 10 or 15 epochs, this image is from the first epoch, first at the starting point, because we cannot identify whether what it is this, right? So in second, maybe after 10 or 15 epochs, it is displayed. Just I have put that particular uh, uh, in between displaying point after particular epochs. So it is showing this particular image, and after again further 10 to 15 epochs, it is showing this particular images, and after, for example, after 50 epochs, it is showing this particular final outcome of what we have written over here, Castle of Host in Heaven. So like this, at every epoch, it is, yeah, we can say after every optimization, at every step, it is showing a particular image which is generated as per our application need. So this was the example of higher variant of GAN. Again, I'm sharing another PPT. Just wait, I'm sharing another PPT. Hope my screen is visible. So as we have seen, many applications of our generative adversarial network. Now there are many challenges for this generative adversarial network. We can discuss with that, so that we can be cautious while designing this particular generative adversarial network, and we'll be having efficient results. So so we can have that first. We can talk about training instability. That is, of course, GANs are known for the difficult training process, and the adversarial setup with generator and discriminator, they are in, we can say, constant competition kind of, because one is saying that to minimize the optimization objective function, and the second one is saying to maximizing the same. So it can cause the instability. So particularly when one component becomes too strong. In this case, which neural network will be becoming stronger? We can say discriminator will be stronger, as discriminator is only distinguishing between the real and the fake. So its training, we can say it's a strong part because its training becomes very faster as compared to our generator part. So this can prevent convergence actually, and affect the overall quality of the generated content, because one will be uh, the two neural networks are not in the syncing of its training one. So to address this, we are having many variants. For example, Wasserton GAN, WGAN. This was introduced, and which stabilizes this training of with a different loss function. Actually, various variants of GANs are there, which are using different loss function and different optimizer for having that particular efficient results for the GAN, which we have already discussed in the application part. So, and additionally, feature matching and progressive growth of the model, these was embedded into these neural networks so that instability can be overcome. So after this training instability, mode collapse problem is there. So this happens when the generator learns to produce only a limited variety of outputs. Sometimes we can see if we have prompted that generate the image of a cat. So it might be same type of cat is it is generating. So it must be ignored actually. We actually it must be avoided, and it can be of course this is a critical problem, because generator is used to generate a real type of value. So if it is generating same kind of cat or same kind of picture, so it means it is not giving a very good result. So to tackle this, mini batch discrimination can be used, or we can use unrolled GANs in that. So these type of variations can be used so that this problem can be. Of course, there are other models also which are avoiding this mode collapse problem. Another challenge we face is the vanishing gradient problem. This occurs when the discriminator becomes too powerful. As we know that discriminator is, of course, the powerful side of neural network. So it makes the gradient of the generator very small. So, and ultimately it will be having that vanishing gradient problem. Again, the solution is like in instability problem, we use WGAN. WGAN can just it can remove this particular problem again. Next challenge is high computational cost. GAN require, of course, as I have already told you, that it takes many hours to train a particular generator and discriminator. So GANs require significant computational resources. So particularly, of course, when we are focusing on high resolution image generation. So to manage this, one approach can be to start with the low resolution images, and during training, and gradually we can increase the resolution in between. So this using mixed precision training. So many variations are there. With the help of that, we can uh, just avoid this again high computational cost problem. Again, I have shown you one example of this uh, ghost castle I have shown. This that particular variant was also designed for resource constrained uh, laptop, we can say, or of course that was not for mobile, but yes, it didn't require any NVIDIA system. Next challenge can be evaluation challenges, as there is no universally accepted metric to assess the quality of GAN generated content. Of course, it is just having the prediction of that value. So to address this, we can have again precision recall values and some other parameters by which we can have some estimate of the precision of this particular quality of that particular output generated by the generator side. Next challenge is hyperparameter sensitivity. Actually, as we know, there are hyperparameters, and GANs actually are very highly sensitive to small changes in hyperparameters. Generally, in neural network, it's not necessary that we are changing the hyperparameters and it is the output will be drastically changing. But in the case of GAN, actually, if we are changing slightly a particular hyperparameter, the result will be totally, it can change the result totally. So it becomes very crucial to have appropriate hyperparameters for these training of generator and this discriminator. Next is we are having data dependency. GANs typically, actually, it requires, because we know that it works on large data set. So if there are a large data set is not there, so we need to augment the data so that learning will be good and efficient result will be there. So if the data is less, of course, the result will not be efficient. That's the general one. So next is the ethical concerns. As we know, deepfakes technology is there, and we are not sure about whether the data is real or the fake one. So this is the major concern when we are dealing with the generative adversarial network. Of course, there must be some detection algorithm. We can they can be used to check whether that value, that image or video or any content is real or fake. So ethical concern must be there. It may be that a policy must be there so that the people will be avoiding to use a particular this generated data. That is the only solution for it. So last we can discuss lack of interpretability. It's another challenge. Like many deep learning models, often these are often viewed as a black box model kind of. So which makes it hard to understand how a decision is taken to for the generated image as in other neural networks. So to address this, uh, it may be that some visualizing intermediate layer can be there, and we can be having saliency maps so that we'll be having uh, in between visualization of the data for that. So these are few of the challenges when we are using generative adversarial network. Uh, if these are taken care of, then the model can be converged very efficiently. I will say not very easily, but yes, there are many constraints. After that, only we can uh, guarantee to have the efficient result out of it. Again, we can discuss about the GAN variants because as we have seen, I have shown you the simple GAN model, but we are having many variants because our applications are very vast, and depending upon our application, we'll be using different variants so that different applications can be designed. So first one is the conditional GAN. This approach adds an extra layer of control to the generation process by conditioning the generator on additional information like a class label. Instead of just feeding random noise to the generator, we also provide it with the condition. So, and this condition can be a label, for example, specifying which type of object should be generated. This allows the generator to produce specific outputs like generating a dog when the label is dog or cat when the label is cat. So application of conditional GAN are of course very vast, from generating images based on text description to creating images based on certain attributes like we can say gender, age. As we have seen in the application, we will be writing for this particular age, we want a particular person face, then it will be giving that particular percentage. So this can be done with the help of this conditional GAN. Next, deep convolutional GAN, DC GAN. it introduced the use of convolutional layer in both the generator and discriminator, which actually improved the quality of generated images. And it also replaced traditionally fully connected layer, which tend to require too many parameters, with convolutional layer that are more efficient for image data. And one of the key feature of DC-CAN is the use of leaky relu activation function and batch normalization, which help stabilization of that training. That I have shown you in the previous slide, which was showing that generator is using that DC GAN sign. So through DC GAN, GANs become much more reliable in generating this high quality images. Although I told you that any kind of neural network can be used, but this DC GAN, basically this DC GAN is giving the very good results. Next is the InfoGAN, which is more interpretable version of GAN. InfoGAN, it focuses on learning interpretable latent representation. What this means is that it tries to find a way to encode meaningful information in the latent space so that specific attributes of the generated image like rotation, scale, color, these features can be controlled. So by maximizing this mutual information between input noise and generated image, InfoGAN allows us to have more controlled features. So we can different views I have shown to you in the application part. So it was rotated, a right view, left view, and different views were generated. And that was with the help of InfoGAN. Next is Wasserstein GAN, WGAN. So this one of the most significant problem with standard GAN is mode collapse, which I have already discussed with you during the challenges, where the generator produces a limited variety of outputs. Of course, for example, again, it is showing again same type of cat or dog or any table or something, or other problem, vanishing gradient. So where the network stops learning effectively. So both of these problems are solved with the help of this Wasserstein GAN. So WGAN addresses these issues. Actually, it is using different distance metric, which is named as Wasserstein distance. That's why it is called Wasserstein GAN. So this this training process with the help of this metric to generate more diverse and realistic images. So it removes that problem of mode collapse. Next is cycle GAN. It allows us to learn mapping between two domains without paired data. In other words, we can say it can transform image from one style to another. And it is not needing that both the pair of corresponding. For example, it can convert photographs into painting, which I have shown you in the application part, or day images into night images. So we don't have both of these, night scene and day scene. We don't require. We just require that particular painting, and it is, for example, day image, and it is converted to night image. So actually, it's been widely used for photo enhancement, artistic creation, and all. So this can be done with this variant. Next is progressive GAN. This is another important advancement with GAN, which improves the quality of generated images by adding layers progressively during the training process. So instead of trying to generate a high resolution image, we are not expecting that high resolution image from the start. The model first generates low resolution image, then progressively adds more layer to generate high resolution image. So this gradual training process allows the model to create high resolution images, of course, which will be almost realistic photograph. So progressive GAN it has been widely applied in face generation and realistic photo rendering. So progressive GAN is really wonderful in creation of that very good quality image with less resources. Next is auxiliary classifier GAN. So this architecture combines the idea of GANs with auxiliary classifiers actually. And in addition to predicting whether an image is real or fake, the discriminator in ASC GAN also predicts class labels. So it means it will be generating that, and it is predicting the class label also. So this allows the model to generate images conditioned on specific categories. And it improves the quality of generated images by providing additional guidance to the discriminator. So it's particularly useful when you need to generate class specific images. Again, like age or gender. The next is the stack GAN. It is another very exciting development in GAN. This model generates images in two stages. In the first stage, some low resolution image is generated from the input text, and stage two, it will refine that particular image which has been generated by stage one. So this method is great for fine-grained image synthesis when really we will be needing some high resolution image. And for example, you could generate an image of a red bird with a yellow beak. So we are very specific about that. So maybe in the first stage, basic structure of the bird will be generated, and in the second stage, this refinement with the color and all features will be generated. So it works in stages. Last is the style GAN. We have style GAN, a truly innovative GAN, of course, we can say. It introduces the concept of style vector, which separates the style of the image from the content. So by adjusting these styles vector, we can control various aspects of the generated images, such as texture, lighting, facial expressions. So, and of course, we can change that, but underlying structure, underlying content will remain same with that. So style again has become a popular choice uh, when we are creating photorealistic human faces, and has been used in a range of creative applications from art generation to character design, which we have already referred to the application part. So each of these advancement contributes to making GANs more stable, interpretable, and efficient, which allow them to tackle increasingly complex tasks. Of course, we have seen that generator training is very complex, and these different variants will help to have efficient output out of that generated uh, images, we can say, or generated videos, we can say. So that was all about GANs. We have studied the GAN architecture, applications, and its challenges and its future scope. We can't say, we can say yes, different variants are there so that we can have better results. So of course, we always think that generative AI is not good, but of course, generative AI is good. But uh, as Sundar Pichai quote is there, the future of AI is not about replacing humans, but augmenting human potential. So we can use that uh, to increase our potential. So thank you all. That's all from my side. Of course, if you want to contact to me, these are my mail IDs. So we'll be starting the next session at 3:30 after 5 minutes.
Thank you, ma'am. Hello, everyone. We will be starting in next 4 minutes.